Okay, organic chemistry 2341. This is the last video for chapter 11. We're specifically going to be talking about reactions with epoxies. Okay, just to remind you what epoxies are cyclic ethers. They have a three-membered ring and oxygen is part of that ring. And they can either be called oxocyclopropanes because the oxygen is part of the ring, oxiranes, or occasionally their common name is typically something, an alkene oxide. Okay, so let's look into a little bit more about these epoxies. These epoxies are cyclic ethers that have a three-membered ring. Besides being called the oxiranes and ethylene oxides, the oxocyclohexane or oxocycloalkane is what they're typically referred to in our UPAC name. Now, because it's a three-membered ring, we have a carbon-oxygen carbon bond angle of only 60 degrees. Remember, we want 109.5 degrees, so that 60 degrees means we have tremendous amount of ring strain associated with having it in this locked position, okay? So let's look at naming these things. The common names, because they're typically made from the oxidation of an alkene, they typically use whatever alkene you had plus the word oxide. So for example, if we were to make the simplest one out of ethylene, we would call that ethylene oxide. If we were to extend that chain to propylene or heptylene, we would then call it propylene or heptylene oxide, okay? Systematically, we typically use the name oxirane. Oxirane specifically means a three-membered ring that we have. And being oxygen is in the ring, it always takes position number one. Okay, so when we look at this right here, our oxygen is number one, and then we number our substituents from the lowest number down. So in the case of this compound here, this is our one position, this is our two position, this is our three position. Therefore, this ethyl group is on our 2 carbon, which means we have 2 ethyl oxirane. Okay, in this case here, our 1 is still the oxygen, and we have 2, 3. We have methyl group on each side, so we have dimethyl. So we have 1, so we have 2, 3 dimethyl oxirane. And if we had both substituents on the same carbon, we would name both of them as the 2,2 dimethyl oxirane. Okay. So occasionally, if you don't want to use the oxirane, we can use the exact same thing where we name the alkane and then the word epoxy. So for example, if we just had epoxy, there would be nothing there, or ethyl epoxy, etc. Okay, so there's 2 different ways we're going to use to form these epoxies. The first one is a ring closing reaction from a halohydrin. Remember, when we take an alkene and react an acid in the presence, a halogen in the presence of water, we can get a halogen on one carbon and the hydroxide on the adjacent carbon. So if we do this halohydrin reaction on an alkene, we'll end up with a hydroxy group and then a halo group on the other one. We can use then a very strong base to deprotonate the alcohol, and then we do an intramolecular SN2 reaction to close that ring and displace the halide here. So that's one way to do it, is this strong internal cyclization. The other way to do it, and it's kind of indicated by the idea that we would call these ethylene oxides because they're done that way in industry, is we actually oxidize an alkene using a peracid. The most common peracid we use is called metachloropurbenzoic acid, or MCPBA. Okay, and what this does is this creates that oxide from the double bond directly. All right, let's look at that mechanism more carefully. Okay, now you might think that it's going to form something and then unform something, etc. But actually, what happens is we can form this 5-membered intermediate here with our peracid, and the electrons will come around, grab the hydrogen out here. The oxygen is then added across the double bond, and we end up with our carboxylic acid here, and it transfers the oxygen directly. This happens all in one step. The reason we know this happens in one step is because the products we get are all syn addition of the oxygen to the double bond. So what that means is if we start with a cis alkene here, we always get the cis epoxy. If we start with a trans alkene, we always get the trans epoxy. That indicates that we're doing that transfer all at once. We don't have time to rearrange. We don't have a ring open that can then rotate. So again, it's a syn addition of that oxidative transfer. It happens all at one time. All right, now that we have our epoxy, let's look at some of its reactivity, okay? So because that ring is strained, the most likely thing for it to do is to have something come in and open that ring up. And so we're going to get addition of a compound to the one of the carbons where the hydroxide will end up on the second carbon. So we have two different mechanisms we can use for this ring opening. The first one is if we have a strong nucleophile, what it can do and that strong nucleophile happens to be in the absence of an acid, we have it come in and do a nucleophilic displacement reaction and ring open reaction. However, in the presence of an acid and a weaker nucleophile, we get a different mechanism. It'll still open the ring and it'll still produce different, but it produces different products, okay? So let's look at what the products are and what the mechanism is, okay? So in the case of ring opening epoxides in the presence of a base and strong nucleophile, we end up with a backside SN2 attack on the least substituted carbon. So in this case right here, we have two methyl groups over here, meaning that our nucleophile is going to come and attack the least substituted carbon, yielding our more substituted alcohol here. So in this case, we end up with a tertiary alcohol created from our system, and our nucleophile is on our least substituted carbon. Okay, because this is an SN2 attack, sterics is the driving factor. Note, this only happens in the presence of base and in the presence of strong nucleophiles. Okay, so if this takes place because of sterics and you end up with your more substituted alcohol, then in the presence of acids, we must have to change the mechanism. Okay, so let's look at that mechanism. When we do this ring opening in the presence of acid, what happens first is in most acid reactions, you end up protonating something first. So in this case, we end up protonating the oxygen of the oxirane. And in that case, now that we have this oxygen protonated, that means that we have now polarized our bonds between our oxygen and our carbon. And so we have an opportunity of having a partially positive carbon on either on one of the carbons or partially positive on the other carbon. So this all goes to carbocation stability, okay? Because the more substituted partially positive charge is more stable, because the more substituted carbocation is more stable, we end up getting attacked by weaker nucleophiles to that more stabilized partial charge. Therefore, it actually ends up substituting on the more substituted carbon. And therefore, the major product formed is our nucleophile attacking our more substituted carbon and our alcohol being on our less substituted carbon, typically giving a primary or secondary alcohol. Okay. Note, if we had it try to attack the other way, this is the less stable carbocation. Therefore, it doesn't progress in that, giving us the more substituted alcohol. So we have a base catalyzed system giving us our steric product and our more substituted alcohol. We have our acid catalyzed system giving us our carbocation stabilized intermediate, which gives us our least substituted alcohol. So it's nice and consistent about which way we're going to get substitution on our products with our nucleophiles. Okay, and the last thing I want to talk about here is that in the ring opening of epoxies, if we did it with acid catalyzed water, what we're going to end up with is we're going to end up with the anti-addition or the trans diol. Remember when we did the oxidation of alkenes with permanganate or with osmium tetroxide, we always got syn addition, and so we got cis hydroxy products right here. When we do this with our epoxy, the epoxy is on one side of the ring. We always get attack on the other side of the ring. So if we use acid catalyzed hydrolysis, we will end up with our anti-addition of our hydroxide, and therefore we'll get our trans dihydroxy product. Okay, I hope you like the introduction to epoxy chemistry. It's all about nucleophilic ring opening, and we have two different mechanisms to work with here. All right.